Now that we are done dealing with some introduction and motivation behind stochastic processes, from this video onwards, we'll be talking about some mathematical foundations of stochastic processes, especially talking about probability. So it's more like a kind of review of probability. By the way, I have a whole playlist on probability. You want to check that out. Okay, so in this first video on probability review, right, we'll be looking at probability spaces, though we've started seeing it in previous videos already. So, probability spaces, this lesson introduces the mathematical structure used to model randomness in probability theory. So, I mean, if you follow Devlin's definition of mathematics as the science of patterns, so you want to see probability as a science, as the pattern of chance, a pattern of chance. And since stochastic processes actually, you have elements of randomness in dynamical systems or randomness in systems that evolve over time. So you need some probability with which you can actually make certain assertions. So here we study sample spaces, events, sigma algebras, probability measures, complete probability spaces, worked examples, and computational verification using Python will be considered. All right, so let's talk about probability space, which we've talked about previously, but I mean, it's good to emphasize some of these things to drive home the point. So talking about the probability space, we say it is a probability space is a triple omega, F, and P, where omega is the sample space. F is the sigma algebra of events, and P is the probability measure. So when you put together the sample space, the sigma algebra of events, or if you like, you can call that the event space. Then, with the probability measure, then you can say you have a probability space. And the interpretation of all of that is this: this omega is the set of all possible outcomes. F is the collection of events, and P is the function assigning probabilities. So, talking about the sample space, right? A sample space is the set of all possible outcomes of an experiment. Imagine if omega is omega, small omega, big omega is small omega 1, omega 2, omega 3, and so on. For instance, we have a coin toss. When you toss a coin, omega is head or tail. When you toss a coin, you either have a head or you have a tail. Then, if you have a dice roll, the sample space is 1, 2, 3, 4, 5, 6, because a die has six faces with these three markings on each, with these six markings on the faces, right? Example, you can also have a continuous experiment where you choose a real number between 0 and 1. So this is continuous. So you have infinite numbers between 0 and 1. You can't know all of them. As far as you're dealing with real numbers, right? You can have 0.01, 0.02, 0. I mean, infinite like that. So that's why it's continuous in that sense. So the sample space is the set of all possible outcomes of an experiment. And then we move on to talk about events. We talked about sigma algebra of events, or if you like, you can call that the event space. So an event rather, is any subset of the sample space. So any subset of the sample space you have is an event. So an event occurs if the outcome lies in that subset. So if an outcome lies in the subset, then you say you have an event. So an event is a possibility in a sample space. So if you roll a die, for instance, so the fact one is an event, two is an event, three is an event, four is an event, five is an event, six is an event. An event is a possibility that you can have in a sample space. So if the event you are concerned with in the role of a die is even number, in that case you have three possible events, that's 2, 4, and 6. And then talking about odd number, you have 1, 3, and 5. Talking about number greater than 4, you have 5 and 6. Talking about a perfect square, let me add that to it, in fact. So if you are interested in a perfect square, what do you get? Okay, I'll just copy this and paste. Then I'll say now perfect square. So which of the numbers from 1 to 6 is a perfect square? That's simply 1 and 4. Okay, so if you're looking for a perfect square, you have 1 and 4 like that. So did I say okay, I just wrote perfect square. I mean to say perfect square like that, and then that's what you get. Right. So we then go ahead to talk about event operations. So so far we've talked about sample space. Now we've talked about an event. An event is a possibility you have in a sample space. Any possible things you can get from a sample space is an event. So event operations, events follow standard set operations like union A union B, intersection A intersection B, complement A complement. For example, if you have A to be 2, 4, 6 and B to be 4, 5, 6, then A intersection B will simply be 4 and 6. That is that what is common to both of them, like that. So then we talk about sigma algebra, which is which is part of the probability space. A sigma algebra F is a collection of subsets of omega. That is, a sigma algebra F is a collection of subsets of the sample space satisfying three properties. First of all, the sample space is included. That is, the whole sample space is included. One. Then it is also closed under complement. So if A belongs to the sigma algebra F, then the complement of A also belongs there automatically. Then number three is that it is closed. So we say the sample space is included first, closed under complement. So if you have something in the sample space in the sigma algebra, the complement of that thing is also there. Then it is also closed under countable unions. So if you have A1, A2, A3 belonging to the sigma algebra, then the union of all the union of A also belongs to the sigma algebra. Now, some consequences of sigma algebra rules from the axioms we obtain that empty set belongs to the sigma algebra. So the empty set. So what have we said now? We already know that the sample space is included. That is, everything in the sample space is also part of the sigma algebra. Then we have also now we are seeing, based on all the rules now, that empty set belongs to the sigma algebra. So the empty set belongs to the sigma algebra, and it is closed under countable intersections. That is, the intersection of all possibilities is also found in the sigma algebra. So let's take an example to drive home the point. So if you let omega to be 1, 2, 3, this is a sample space 1, 2, 3. One possible sigma algebra will be the empty set and the sample space itself. Then the other possibilities, you have 1, you have 2, 3, like that. So verification, you see that sigma is included, then complements are included. If you take 1 now, the complement of 1 will be 2 and 3. You have that here automatically. Then unions are also included. So the union of 1, 2, 3 is automatic. The union of the empty and 1, right, is actually 1. The union of 1 and 2, 3 is 1, 2, 3, which is this one. So union of omega and any one is omega itself, So unions are included like that. So then we talk about important types of sigma algebras. So you can have the trivial sigma algebra, which contains just the empty set and the event space and the sample space rather. So you have the empty set and the sample space. So only two events. You have the impossible event and the certain event, basically. That's the trivial sigma algebra. Then you have the power set sigma algebra, which is 2 raised to power 2 raised to the power of the sample space, like that. So in this case now, all subsets are events. Example for a dice now. There are 2 raised to power 6. So for a die, if you have a die, so you have 2 raised to power 6. That means 64 possible events for when you have a die, like you toss 2 dice. So you have 2 raised to power 6, and that goes to 64. So then we talk about probability measure now. So a probability measure is a function P such that F is mapped to the set, the closed interval 0 to 1, 0, comma 1, which assigns the probability to each event. So probability to 1, 0, a probability to 1. So you have Kolmogorov axioms for probability measure. A probability measure must satisfy 3 axioms. Number 1, a probability measure must be non-negative. So non-negativity is the first one. That is, if you are looking for probability and you get a negative value, something is wrong somewhere, definitely. So a probability is non-negative, and so that's why probability is between 0 and 1. So the lowest probability you can never get is 0, and the highest you can never get is 1. So if you get any probability that is negative, something is wrong somewhere for sure. So you want to check why you are getting that kind of result, definitely. So because something is wrong. So lowest probability is 0 and highest probability is 1. So if you have negative probability on any probability, like 1.001 or like 1.1, that something is wrong somewhere. Then there's also normalization. So the probability of the whole sample space is equal to 1. right? So that means if you add up the probability of all the possible events in the sample space, everything goes to one. Then you have the countable additivity. So if you have disjoint events like AI intersection AJ, it is empty because they have nothing in common. In that case, now you then have the probability of the union of all the possible AIs ends up giving you the summation of from I equals 1 to infinity of all the probabilities of A sub I. And of course, I see that leading to this value of 1 when you add all the possible probabilities like that. So that's the Kolmogorov axioms for probability measure, non-negativity, normalization, and countable additivity. So an example of a probability space now, we already know that probability space is a triple containing, first of all, the sample space omega, the sigma algebra, or if you like, the event space F, and of course the probability measure. So let's look at example of probability space then. So you have a coin toss experiment. So the sample space for a single coin, that's head or tail. Then the sigma algebra, which you can also call the event space, that'll be the empty and the omega, then H and T. So H, the complement of H is T, the complement of T is H, and then empty union H is H. Then omega union anyone remains omega like that. Then you have probability measure. Now, probability that you're going to get a head when you toss a coin is 0.5. Probability you're going to get a tail is 0.5. And then, thus, in this case now, H, comma T, then this F now, and of course, the probability measures all form a probability space. So the probability space is a triple of omega, F, and P, probability measure in that sense. So we have a worked example here talking about a dice. So you have a sample space 1, 2, 3, 4, 5, 6. So if you are for events now, if the events you're looking for are even numbers, so you have A to be 2, 4, 6. So the probability that you get an even number in that case will now be, so there are three even numbers there. So that's 3 out of 6, which is 0.5. So if you are looking for an event that yes, that the whatever you roll on a die is going to be greater than 4, there are two possibilities. Only 5 and 6 are greater than 4. So you have two possibilities out of 6. So that will give you 1 over 3 at the end of the day. Then you can have intersection of events, right? So for A is 2, 4, 6 and B is 5, 6. So the intersection of A and B is simply 6 because 6 is common to both. So if you are looking for the intersection of these two events, then that'll be 1 out of 6 like that. So, and of course we can simulate that here. See, probability of A is 0.505 because probability of A is 3 out of 6, right? So that's 0.5. You can see those decimals are trailing because of the way the computation is going. And probability of B, you have 2 out of 6. That's 1 over 3. That's roughly 0.3333. And probability of the intersection of both of them will be 0.16581. That's basically 1 over 6 like that. So if you run that, then we go on to talk about continuous probability space. So for continuous probability space now, we have an example. If you choose a number between 0 and 1, then so that the sample space is this closed interval 0 to 1. So for the sigma algebra now, you have all Borel sets. So in that case now you have the uniform probability measure such that probability of the intersection A to B is B minus A. So an example is probability of the closed interval 0.2 to 0.5 is 0.3. Now this is taking us into something like Lebesgue measure and all of that, right? So, and if we simulate that, we see that we get the same answer. So if you take n to be 1 million, right? And then x is random of this 1 million. So at the end of the day, you have A is equal to x less than 0.3. In that case now, the estimated probability, the average estimated probability like that is going to be 0.3, which we got here. That's the difference between 0.5 and 0.2, like that. And then we move on to talk about complete probability space. Okay, so a probability model consists of omega, F, and P, where omega talks about the outcomes, that's the sample space. F talks about the measurable events. If you like, call it the events, space, and you have P, which is a probability measure. That gives you a complete probability space. Now the question is, why sigma algebras are necessary? In continuous spaces, not all subsets can be assigned probabilities consistently. So sigma algebras ensure probabilities remain consistent, limits of events remain measurable, and integration is well defined. So this connects probability theory to measure theory and Lebesgue integration. So far, I've taken care of probability theory on my channel, but I've not done measure theory and Lebesgue. Maybe at some point I have to do Lebesgue measures, or I talk about measure theory overall, right? So with that, we come to the practice problems. Solve the following problems unless otherwise stated. Assume finite sample spaces. So a coin is tossed once. Define the sample space. Of course, that the sample spaces will consist of one, two, three, one a coin head and tail. Of course, list of possible events if the sigma algebra is the power set. So in that case, you have the empty set, you have head, you have tail, and you have the sample space omega itself. Then two, a fair die is rolled. Let A be the event even number. So when a fair die is rolled, there are three even numbers possible. So the probability of A will just be 3 out of 6, which is 0.5 easily. So for a die roll, define A to be 1, 2, 3, and B is 3, 4, 6. So A union B, of course, A union B will just be 1, 2, 3, 4, 5. That's all. A intersection B will be uh just 3, because only 3 is common to both. Then A complement, that is, if you take away 1, 2, 3, you automatically get 3, 4. A complement, that's 1, 2, 3 now. For a die roll, right? So 1, 2, 3. If you take 1, 2, 3 out, you have 4, 5, 6 left. That's A complement right there. Then let the sample space be ABC. Is the collection F a sigma algebra? Excellently, yes, because you have A here, you have the empty, you have A, then you have BC together because A complement is BC, BC complement is A, and then you have the complete space. So that is actually the sigma algebra. I've given you the justification by the explanation I made. Then for question 5, let sigma let omega be 1, comma 2. List all sigma algebras on omega. That'll be empty, 1, 2, and of course, the whole thing itself, the whole event space. 6, suppose we have this. How many elements are in the power of 2 omega? Of course, that'll be 2 raised to power 4, which is 16, I believe. Yeah, that's 16. Then 7. So you have question 7 now. Let events A and B satisfy. Probability of A is 0.4, probability of B is 0.3. So probability A intersection B is 0.1. So you now need to compute probability A union B. Okay, I think this is a very important thing to look at. So we need probability A union B. Probability A union B. Okay. So I believe probability A union B. Okay, I guess let me write at this point. I've been trying to avoid to write, but I think it's time to write now. Probability of A is 0.4. Okay, I guess I need to snip it and bring it over here. So where's the snipping tool? Right here. So this is what we have, and I take it to the worksheet. Okay, so A and B satisfy. Probability of A is 0.4, probability of B is 0.3, probability of A intersection B is 0.1. So we want to compute A intersection B. So I think this is easier to imagine when we draw it as a Venn diagram. So you have A, you have B. So this is A, this is B. Okay. So um you definitely have an intersection here. So probability of A. So let's say, of course, this region is A, like this. And then this intersection. Okay, how do I even put it now? So here, this is like this is this is A. Okay, that is A. Then this is B. That's just B alone, right? But guess what? This is the intersection between A and B. This is A intersection B. Okay, so and What we now need is A union B. A union B is everything, the whole thing together. Okay? So if you understand what is going on here, you will discover that if you want to represent it as a region, so it means that we have, so um, as a set now, this is, okay, we don't even need this. So you have this, you have this. So it means that uh, this is A, this is B. So probability of A is equal to 0.4. Probability B is equal to 0.3. And we have probability um, A intersection B, that's A intersection B there, is 0.1. And we are looking for the whole region now. Okay? We are looking for everything. We are now looking for A union B. So in essence, you discover that um, probability of A. Oh, okay, I think this is not representing it the way I would have expected. So this is looking like they are not interconnected. Okay, even this, I think I need to re-explain this. That's not accurate. So you have A, you have B. Okay, so now what I'm supposed to say is the whole of this is A, right? Yeah, I think this is a better way to look at it. And the whole of this is B. Nice. Everything still encroaches. Now you now have this region where you now have a point. You have this region where both blue and red, green and red lines are meeting. That is A intersection B. So in essence now, you now discover, so it means that probability A, okay, the probability of the whole A is 0.4. Probability of the whole B is 0.3. And then this intersection between the probability A intersection B is equal to 0.1. So and we are looking for probability A union B. So we say that probability A union B, like that, is equal to probability of A, which is the whole of A. But you see, inside the intersection is there. Then plus probability of B. Inside B, the intersection is still there. Because the intersection is appearing twice and we want it to appear only once, right? So we then have to subtract. We now have to subtract. So we want A union B, which is everything. So and A union B has appeared in A, it has appeared in B. So we have to remove one of it. That's probability A intersection B. So now probability A union B is probability A, which is 0.4, probability B, which is 0.3, probability A intersection, which is 0.1. So at the end of the day, we have 0.7 minus 0.1, that is 0.6. So probability A union B is simply 0.6, like that. Okay, so you remove the intersection, because it's appearing twice. So look at 8 now. Probability of A is 0.7. So we need to compute probability A intersection C. Okay. So this is how that goes. Probability of A. So if you look at it as a set again, so you have A in a particular set. So now this is A. This is A right here. Inside here is A. But outside here is A complement. Everywhere else around that circle is A complement. So in essence, we know that probability A plus probability A complement is equal to 1, right? And we've been given probability A to be 0.7, I believe. Probability A is 0.7, okay? So probability A is 0.7, then we need probability A complement. And so adding the two, you have 1. So probability A complement is equal to 1 minus 0.7. So that means probability A complement is 0.3. Easily so. And then, yeah, I guess I need to keep moving. So number 9 now says let A1, A2, A3 be all that be disjoint event with probability is this. So you want to compute A1, A2, A3 because they are disjoint, you don't need to remove anything, just add them up. That's 0.2 plus 0.3 plus 0.1, that's 0.6 again. Then question 10, a fair die is rolled. Find the probability of the event number greater than 3. So for a fair die, you have 1, 2, 3, 4, 5, 6. Any number greater than 3 will be 4, 5, and 6. So that will be 3 over 6 easily. 11. So let the sample space be 1, 2, 3, 4. Define probability P of 1, 0.1, probability P of 2 is 0.2, probability P of 3 is 0.3. Then you now need to find probability 4 so that the P is a probability measure. For P to be a probability measure, it means all the possible probabilities will add up to 1. So it means you have P of 1 plus P of 2 plus P of 3 plus P of 4 equals 1. So since you have these three, now that's 0. This is 0.6. So it's more like you have 0.6 plus P of 4 equals 1. So P of 4 will be 1 minus 0.6, so P of 4 will be 0.4 easily. Okay, because all probabilities must add up to 1. That's the normalization we saw the other time. Suppose the sample space is h comma t, with probability of head is 0.6, probability of tail is 0.4. So compute probability of omega. Of course, probability of omega is everything. That's 0.6 plus 0.4, which is simply 1. Then 13, omega is 0 comma 1. So with uniform probability, compute probability 0.2 to 0.7. That's 0.7 minus 0.2, which is simply 0.5 straight up. Then 14, let this be omega. So you want to compute probability this union that. So this is like 0.1, because 0.1 minus 0, that's 0.1, plus 0.6 minus 0.5, that's 0.1. So that's 0.1 plus 0.1, which is equal to 0.2 altogether, like that. So you have 15. P of A is 0.4, P of B is 0.4. So if A and B are disjoint, that means they have nothing in common. So if they didn't have nothing in common, if they had something in common, you have to subtract probability A intersection B, but they have nothing in common. You just add straight. So when they have nothing in common, P of A union B is equal to P of A plus P of B. That's 0.5 plus 0.4, which is 0.9. Question 16. Let A be a subset of B. Show that probability of A is less than or equal to probability of B. Of course, that can go easily because A is a subset of B. So A doesn't have as many elements as B. So that would hold. Then 17. If P of A is 0.8, find the probability that event A does not occur. The probability that is not occur will be 1 minus 0.2, which is 0.2 easily. Question 18, for a die roll event, A is 135. So compute probability of A. Probability of A will simply be 3 out of 6 because it's a die. So 3 possible events. So 1, 2, 3 over 6. That's 0.5. Question 19 and 20 finally. So let omega be 1, 2, 3. Construct the probability measure assigning equal probability to each outcome. So because there are three things now. So probability of 1 will be, so there are three. So probability of 1, you have 1 out over 3, probability of 2, 2 over 1 over 3, probability of 3 is 3 over 3. So that when you add 1 over 3 plus 1 over 3 plus 1 over 3, you get 1 over 3 for each one. I mean, you get 1 overall for the whole thing because probability of omega should always give you 1. So 20, let events satisfy P of A 0.5 and P of B 0.6. What is the minimum possible value of P of A intersection B? Of course, the minimum value this can be will be what is the minimum possible value, okay, of P of A intersection B? Minimum value. Okay, so that means you need 0. So the minimum value is what makes the whole system to be to be 0, I think. Is it okay? I guess I need to set this off. P of A is 0.5, P of B is 0.6. Okay, P of A, P of A, P of A is 0.5, P of B is 0.6. So we need minimum probability of A intersection B. This is an interesting question. So what minimum value can it have? So we know already that so probability of A union B, for instance, should actually be probability of A plus probability of B, right? Plus probability of, I mean, minus rather, minus probability of A intersection B. So, and we need the minimum value of this, right? Okay, the minimum value of this. So the minimum value of this now would mean that the minimum value. Of course, this one cannot be 0 because probability of A union B should be probability of A union B should be less than or equal to 1. That's one sure thing we know. Okay, so for to get the minimum value of this, we need to set this to less than or equal to 1 because the probability of A union B should lie between 0 and 1. So what I'm saying is 0 should be less than or equal to probability of A union B less than or equal to 1. That's what we are saying here. So it's constrained between 0 and 1. So now if we have probability of A is 0.5, probability of B is 0.6, minus probability of A intersection B, that should be less than or equal to 1. So in that case now, we have 0.5 plus 0.6 is 1.1, minus probability A intersection B will have to be at least less than or equal to 1. So in that case, now that means that 1.1 minus 1 is less than or equal to probability A intersection B. Okay, so that means 1.1 minus this, so 0.1 should be less than or equal to probability of A intersection B. So it means that so we are looking for the minimum, right? So that simply means that we can say now that so the probability of A intersection B should be greater than or equal to 0.1. So the minimum value, therefore, the minimum value of probability of A intersection B is 0.1. So if it is bigger than 0.1, we can't have we can't say, because this is already above 1, right? This cannot be, the whole thing cannot be above 1, right? So I think that's how that goes. So with this, we come to the end of this interesting video on probability spaces. Interestingly, I ran through all the 20 questions. That's a rare one. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Don't forget to look at the questions again, try them out, try your hands on them, and see how well you understand the gist. All right. So if you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, the question is why? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges, like getting to see some videos first, or being the only one seeing some videos. Or you can also hang out with me to discuss whatever interests you on my channel. You can also request for PDF copies of my notes in case you want to see hard copies of the things I'm doing. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.